so this is the Honors Chemistry Section 7.1 lesson video. And so in Chapter 7, we are officially going to jump into bonding. So up until now, we've been talking about one atom or ion at a time. And so now we're going to start bonding things. And so that's where we're headed in this unit. So the first thing we need to talk about is ions, because that's one of the ways that atoms bond, is they gain or lose electrons and become ions, and they're attracted to one another. So valence electrons are electrons in the highest occupied energy level. Valence electrons are the only electrons involved in chemical bonding. And elements in the same group have the same number of valence electrons. So you can tell how many valence electrons an atom has based on its location on the periodic table. So every element in group 1 has 1. Group 2 has 2 valence electrons. Group 13 has 3, 14 has 4, 15 has 5, 16 has 6, 17 has 7. Group 18 has 8 except for helium. Helium's in the first energy level, so remember it only has 2 electrons. So helium only has 2, so that's why I have this arrow here just to point out the exception to the rule. But otherwise you can just find an element on the periodic table and know how many valence electrons it has, because remember, the whole periodic table is based on the electron configuration, and so that's why it's shaped this way. And so that makes a lot of elements in the same column have the similar properties because their electron configurations are similar. So electron dot structures are diagrams that show the symbol of an element surrounded by the valence electrons as dots. So everything in group 1 would have 1 dot because it has 1 valence electron. Everything over here in group 15 would have 5 dots. Everything in group 18 has 8 dots except for helium. Now the important thing to note is that the greatest number of valence electrons you will see is 8. So like you should never be putting more than 8 valence electrons. The other electrons are core electrons. So let's look at a couple together. Alright, so it says write the electron dot structure for the following elements. Well, P is in group 15, so it would have 5 valence electrons. Now some teachers are picky about where you put those 5, like they want you to separate them until you have to pair them. But the point is we're going to be getting to bonding anyway, and so I'm not really worried about where you put them, I'm worried about how many you have. Argon is in group 18, so it has 8 valence electrons, so I will just put 8 around it. Magnesium is in group 2, so I will put 2 valence electrons. And then helium is in group 18, but remember it's the exception because the first energy level only holds 2 electrons. It only has 2 valence electrons. All right, so you can just use the periodic table to figure out how many valence electrons each element has. So the Octet Rule states that atoms tend to achieve a stable configuration when they have 8 valence electrons. Now notice it says they tend to because there are some exceptions to the rules. An octet of electrons consists of full S and P sublevels. So S holds 2, P holds 6, so together that's 8 valence electrons. So when an electron configuration has a full last S and P sublevel, that element is very stable and it's like a noble gas. Metals tend to lose electrons to achieve noble gas configuration, whereas nonmetals tend to gain electrons to achieve noble gas configuration. And that's just based on the amount of valence electrons. The metals are on the left of the periodic table, so they tend to only have maybe 1, 2, or 3 valence electrons out of 8, so they tend to lose those. Whereas nonmetals are on the right of the periodic table, so they have more like 5, 6, 7 valence electrons, so it's easier for them to gain a few to become like a noble gas. And that's what noble gas configuration means. The noble gases are stable. They have full S and P sublevels, and for helium, of course, it's just an S sublevel. So other elements want to be like that. They want to be stable and have full 8 valence electrons also. Transition metals generally do not form ions that have a noble gas configuration. So transition metals in the middle, sometimes they have their own thing going on with that D sublevel. So a cation is a positive ion that has lost electrons. So I like to think of the T as a plus sign. Okay, of course I picked the font where it has the little tail on it, but you know, a T looks like a plus sign. And so it becomes positive by losing electrons. So a loss of electrons from an atom is always an endothermic process. It requires or absorbs energy. So in other words, it requires energy for us to try to take an electron away from an atom. When writing the electron configuration for a cation, you write the electron configuration for the atom and then subtract the electrons from the highest energy level. When you name a cation, the name of the element does not change. So for example, Ca is calcium. Ca with a positive 2 charge is just a calcium ion. So notice I didn't change the word calcium at all. So cations, the name remains the same. Now if you notice, I brought up electron configuration. So we're about to jump into electron configuration again. If you are struggling with that, you need to go back and watch some of the lesson videos from chapter 5. That's where I go into electron configuration. So I'm not going to be pulling up that periodic table again. I'm just going to kind of expect that you got one to look at this point. All right, so if you're struggling with that, maybe go back to chapter 5 first. All right, so now we're going to write the electron configuration and name of the following ions. So here we have Sr, which is strontium, with a positive 2 charge. So before I do anything, I'm just going to disregard the charge completely, and I'm just going to write the electron configuration for just Sr. Okay, so I know at hydrogen I'm at 1s2, at lithium I'm at 2s2, at boron I'm at 2p6, at sodium I'm at 3s2, at aluminum I'm at 3p6, at potassium I'm at 4s2, at scandium I'm at 3d10, at gallium I'm at 4p6, and at rubidium I'm at 5s2. So this is the electron configuration for just strontium. Now of course, before I do anything, I need to rearrange. So I need to rearrange my 3d and my 4s. So 3d10, 4s2. Now, the last thing I have to do is take into account that now it has a charge. So what does a positive 2 charge mean? A positive 2 charge means it lost 2 electrons. So I go to the highest sublevel. Okay, you can't just take them from anywhere. I go to the highest sublevel and I start removing electrons. And then if I need to go to the next one, I can go to that one. All right, so I need to remove 2, so literally I just get rid of 5s2. And so in my class, I'm fine if you write it and just cross it out, or you can erase it. Either one is fine. But make sure the sublevels are in order. All right, and then what do we call this? Well, it's called strontium. So since it has a positive 2 charge, it's still just called strontium, but now it's an ion. So I'm just going to call it strontium ion. And so that's all you do. All right, so next we have iron with a positive 3 charge. And so I wrote my charges differently on purpose to make sure to remember to tell you that like 2 positive and positive 2 mean the same thing. Sometimes you'll see the charge written first, sometimes you'll see the number written first. All right, so I'm just going to write it for iron without taking into account the charge. So iron's Fe, so I start at hydrogen, it's 1s2. Now I'm at lithium, 2s2, boron, 2p6, sodium, 3s2, aluminum, 3p6, potassium, 4s2, scandium, 3d holds 10, but I'm going to stop at Fe. So I do 1 for Sc, 1 for Ti, 1 for V, 1 for Cr, 1 for Nn, and 1 for Fe. So I'm going to end with 3d6. Now let me show you something real quick to show you why it's important to rearrange. Okay, so I'm not going to rearrange just yet. All right, so this is my electron configuration for iron. But it has a positive 3 charge. So that means it has lost 3 electrons. If you don't rearrange, you may be tempted to take your 3 electrons from 3d6 and change that to 3d3. However, that is not the highest level, because if you look, we were supposed to swap 4s and 3d, making 4s the highest level. So that's why if you don't rearrange, sometimes it literally causes you to miss the question. Okay, so it should be 3d6, 4s2. Now I need to lose 3 electrons. Well, I can't take 3 away from 4s2. So I can get rid of 4s2. So that gets rid of 2 electrons. So then I just need to take 1 more. So I just go to my next sublevel. So I need to take 1 from here, so it becomes 3d5, like that. Okay, so if you use all the electrons from the highest energy level, then just go to the next one. All right, and then again, because it's positive, it's still called iron, and then we'll just throw ion at the end of it. Okay, so that's all you do, is you just write the normal electron configuration, and then just take into account the charge and take away those electrons from the highest sublevels possible. All right, so let's move on and look at a couple more. So there's my answers. All right, so maybe pause it and try these two, and then we'll look at it together. So I'll assume you paused it at this point. All right, so next we have gallium, which is Ga with a positive 3 charge. All right, so I'm going to start at hydrogen, so it's 1s2. Now I'm at lithium, 2s2. I'm at boron, 2p6. I'm at sodium, 3s2. I'm at aluminum, 3p6. I'm at potassium, 4s2. I'm at scandium, 3d10. And now I'm at gallium, so 4p1, because I just go to the first element in 4p. Now it has a positive 3 charge, so I need to lose 3 electrons. All right, so we got a positive 3 charge. But before I start taking away, I obviously know I'm going to have to get rid of 4p, but then it's like, okay, well, did I take away from 3d? No, because we have not rearranged yet. Okay, so it's very important to rearrange before you start removing electrons. All right, so I need to rearrange and switch 3d and 4s first. So 3d10, 4s2. All right, so now I can remove my 3 electrons. So I can get rid of 4p1, so that's 1 electron. And then I can get rid of 4s2, so that's my other 2 electrons. So now I remove 3 electrons. All right, and then again, because it's positive, I don't have to change the name. It's gallium, and then I'll just throw ion at the end since it has a charge. All right, so hopefully you got that one right. If not, make sure you try the next one. Okay, I'll assume you've done that. So we have sodium with a positive charge. Whenever you just see positive or negative, the 1 is understood. So this is sodium with a positive 1 charge. So let's just do normal sodium first of all. All right, so I'm going to start at hydrogen, that's 1s2, then lithium, which is 2s2, and then boron, which is 2p6, and then sodium, which is 3s1. All right, so it has a positive charge, which means it lost 1 electron. So I'm going to remove the highest one, which is 3s1. And so then because it's positive, I don't change the name. It's still sodium, and I'm just going to tack ion on at the end. All right, so this is how you do electron configuration for cations or positive ions. So as you can imagine, anions is very similar. So let's look at some of those. So there's my answers. All right, so anions are negatively charged ions, so they have gained electrons. So when we take into account the charge of a negative ion, we need to add extra electrons. The gain of electrons is an exothermic process because you got to think it's really favorable for an electron to attract to a positive nucleus because negative and positive coming together is always favored. So it releases energy. Any kind of favorable process normally releases energy. There's exothermic. Whereas for us to take a negative away from a positive nucleus, that requires energy. When you write the electron configuration for anions, you write the configuration for the atom and then add the correct number of electrons. Now this is where it's slightly different. When you name an anion, you change the ending of the element to "ide." So like Cl is normally chlorine, but once it has a negative charge, it becomes chloride. That's where we get the name for salt, sodium chloride. The sodium's positive, so we just call it sodium, and the chlorine's negative, so we call it chloride. All right, so we have to change the ending if it's an anion. So let's look at a couple together first. So here we have P, which is phosphorus. It has a -3 charge, and so let's just worry about phosphorus right now. So I'm going to start at hydrogen, so it's 1s2. Now I'm at lithium, 2s2. I'm at boron, 2p6. I'm at sodium, 3s2, and I'm at aluminum, 3p. And remember, I'm just going to phosphorus, so I do 1 for Al, Si, P. So I end up with 3p3. I don't need to rearrange because I haven't gotten out of order yet. Remember, you won't get out of order until you hit the first 3d sublevel. All right, and it has a -3 charge, so that means it has gained 3 electrons. Okay, so positive means we've lost electrons, negative means we gained. So instead of 3p3, it's gained 3, so it will end with 3p6. So the most common mistake is people just doing the wrong thing. You see a -3 or a 3 negative charge, so you think subtract 3 in your mind. and so you'll take away 3. But remember, a negative 3 charge means that when you compare protons and electrons, I have 3 extra electrons. So I have an overall net charge of 3 negative. All right, now we do have to change the name because this is negative, so it's not just going to be phosphorus anymore. We have to change the name to ide, so it is the phosphide ion. And in the beginning, I know some of you don't know where to add the ide, like is it phosphoride or whatever, but you'll get used to seeing them. All right, so next one is fluorine with a -1 charge. So I'm just going to write the electron configuration for fluorine first. So I'm going to start at hydrogen, 1s2, lithium, 2s2, and boron, 2p, and then I'm only going to go to F. So I'll do 1 for B, C, N, O, and F. So I end up with 2p5. Again, I don't need to rearrange because I haven't gotten out of order yet. A -1 charge means it has gained 1 electron. So I go to my highest sublevel and I give it 1 extra electron. So it ends up with 2p6. And then because it's negative, instead of being called fluorine at this point, it is called fluoride ion. So you got to add that ide at the end. So negative ions or anions end in ide. All right, so hopefully that wasn't too bad. Hopefully you remember electron configuration from chapter 5 and think this is super easy. All right, so I'll give you a chance to try a couple. So you try these two. We have bromine with a -1, sulfur with a -2, and I will assume you paused it and tried these. So first let's do Br, just as an element. So I'm going to start at hydrogen, so I have 1s2, lithium, 2s2, boron, 2p6, sodium, 3s2, aluminum, 3p6, potassium, 4s2, scandium, 3d10, and gallium, 4p. I'm going to stop at Br. So I have Ga, Ge, As, Se, Br. So I'm going to end with 4p5. But I have to take into account this charge. So it has a -1 charge, so it has gained 1 electron. All right, so instead of ending in 4p5, it needs to end in 4p6. But before I do that, just so we don't forget, here I have gotten to the point where I need to rearrange. So I need to take my 3d10 and 4s2 and swap places. And then I can add my charge. So instead of being 4p5, it's gained an electron and ends in 4p6. Now when we need to name it, instead of being called bromine, since it has a negative charge, it will be called the bromide ion. So we just changed bromine to bromide. So hopefully you got that one right. All right, if you haven't tried the second one, go ahead and do that. I'll assume you've done that now. So now we're at sulfur, which is S. So let's just write the normal electron configuration. So for hydrogen, I have 1s2, lithium, 2s2, boron, 2p6, sodium, 3s2, and aluminum, 3p. And then I'm going to stop at sulfur. So I'm going to do Al, Si, P, and S. So I'm going to end in 3p4. I don't have to rearrange because I didn't make it to where they go out of order yet. So a -2 charge means it gained 2 electrons. So instead of ending in 3p4, it's going to end in 3p6. Now, it's a negative ion, so instead of calling it sulfur, I'm going to call it sulfide. So remember, for positive ions, you are going to take away electrons, and the name stays the same. For negative ions, you're going to add electrons and then change the ending of the element name to ide. So like I said, hopefully you're good at electron configuration and this all makes total sense and you think it's super easy. If not, go back and watch chapter 5 again. Alright, so this says give the chemical symbol including mass number for each of the following ions. So it says an ion with 22 protons, 26 neutrons, and 19 electrons. Well, the protons gives me the identity of the element. That's how I can tell what the element is. So this is the identity. So I have 22 protons, so that means the element is titanium. So Ti. When it says write the symbol including mass number for each of the following ions, I'm going to use shorthand. So my protons go down here. Remember, this is your atomic number. My mass number is protons plus neutrons. So mass number equals protons plus plus neutrons. So 22 plus 26 is 48. So that would be my mass number. And then it says it has 19 electrons. So it has 22 protons, but only 19 electrons. So that means it has lost 3 electrons. So that means it has a 3 positive charge. And so the charge, of course, goes up here. Okay, so this would be this ion. All right, so let's look at the bottom one, or you can try the bottom one on your own. It says the ion of sulfur, so this time they told me what it was at least, so I know it's S, that has 16 neutrons and 18 electrons. So they didn't tell me how many protons, but I know it's sulfur, so I can look at the periodic table and tell that's 16 protons. So I know that the atomic number is 16. I need to do the mass. Well, I can see there's 16 protons and 16 neutrons, so I can tell that's a mass of 32. And then I can see there's 18 electrons. Well, there's only 16 protons, so that means it's gained 2 electrons. So if something gains 2 negatives, it has a 2 negative or a negative 2 charge. And so that would be my symbol for that sulfur ion. All right, so really it's just about remembering what everything means in shorthand. So your symbol, atomic number, which is protons, mass number, which is protons plus neutrons, and then your charge, which you can tell when you compare your protons and your electrons. Once you figure out, did you lose electrons, gain electrons, or is the charge neutral? All right, so hopefully that wasn't that bad either. All right, so maybe pause it and try this one on your own, and then I'll assume you've done that, we can look at it together. So it's how many protons, neutrons, and electrons does this ion possess? All right, so I need protons, which means I need the atomic number. Now that's missing down here, but it's SE, so I can just look at the periodic table. Okay, so I find SE, and I can see the atomic number is 34, so that means there's 34 protons. All right, next I need neutrons. To get neutrons, you just do mass number minus atomic number. That will give you number of neutrons. So I can just do 79 minus 34. That's all I have to do for that. And so then if you look, we get 45. So our neutrons are 45. And then electrons normally equal protons. So normally my electrons would be 34, but I have a 2 negative charge. So that means it's gained 2 electrons. So instead of having 34, it now has 36. Okay, so like I said, for the charge, really it's about making sure you don't think of like a 2 negative as a minus 2, like as a subtracting 2. You think of it as 2 extra negatives, so there's 2 extra electrons. All right, and there's my answer. So it says predict the charge, oh that should say charge, sorry. Predict the charge expected for the most stable ion of barium and for the most stable ion of oxygen. Okay, so y'all, to do charges, you can just look at the periodic table. Okay, so we talked about charges back in chapter 6. So everything in group 1 tends to have a positive 1 charge because it will lose its 1 valence electron. Everything in group 2 has a positive 2 charge. The transition metals just tend to have different positive charges. Sorry. Group 13, they have 3 valence electrons, so they tend to lose those and have a positive 3 charge. Group 14 has 4 valence electrons. They can either lose 4 or gain 4 to get 8. So they have a positive or negative 4 charge. Group 15 has 5 valence electrons, so they tend to gain 3 and have a negative 3 charge. Group 16 has 6 valence electrons, so they tend to gain 2 and have a negative 2 charge. Group 17 has 7 valence electrons, so they tend to gain 1 and have a negative 1 charge. And group 18 has 8 valence electrons, or helium has 2. And so since they're already full, they're stable and have a 0 charge. Alright, so most stable for barium, barium is in group 2, so it would have a positive 2 charge. And oxygen. Oxygen is in group 16, so it would have a negative 2 charge. And so you can know charges just based on what group an element is in. So there's my answers. So maybe pause it and you try the next one, and then I'll assume you've done that. We'll look at it together. So it says predict the charge expected for the most stable ion of aluminum. So aluminum is in group 13, so it would have a positive 3 charge. Fluorine is in group 17, so it would have a negative 1 charge. And of course, remember that one's understood, so I don't usually write it. Alright, so hopefully you got those right. And like I said, you can just look at an element on the periodic table as long as it's not a transition metal or other element that has more than 1 charge, and you can tell the charge just based on its location. So, section assessment. It says, how can you determine the number of valence electrons in an atom of a representative element? You can look at the group that it's in. Number 2, atoms of which elements tend to gain electrons? Well, the ones that tend to gain electrons have negative charges, and those are the nonmetals, or the right of the periodic table. And then atoms of which elements tend to lose electrons? Well, the positives tend to be on the left of the periodic table, and those are the metals. Number 3, how do cations form? Well, first of all, a cation is a positive ion. So how does something become positive? It loses electrons. And then how do anions form? Well, anions are negative ions. So how does something become negative? It gains electrons. All right, number 5 and 6 actually kind of go together, so I kind of just put them together in class all the time. Because this one says how many valence electrons are in each atom, and this one says do the electron dot structure, which that's practically the same thing. So we're just going to kind of do number 6 as number 5 and just go from there. So potassium, the symbol is K. It's in group 1, so it would have 1 valence electron, and that would be its electron dot structure. Carbon is C. It's in group 14, so it has 4 valence electrons, and that would be its electron dot structure. Again, you would need to check with your teacher as to whether they're picky if you split those 4 up or not. Next one is magnesium. It's Mg. It's in group 2, so that would be 2 valence electrons, and there's the electron dot structure. And oxygen is in group 6, so it has, it's in group 16, so it has 6 valence electrons, and so that would be its electron dot structure. All right, so far, hopefully so easy. So let's move on. Alright, so it says how many electrons will each element gain or lose in forming an ion? So all you need to do is figure out what the charge is, and then that will tell you what it will gain or lose. So real quick, let me just put our makeshift periodic table up here again. So remember, everything group 1 is positive 1, positive 2. All our transition metals are positive something. Then we have positive 3, plus or minus 4, minus 3, minus 2, minus 1, and 0. So calcium is in group 2. That means it has a positive 2 charge. So that means it's going to lose 2 electrons. Fluorine is in group 17, so it forms a negative 1 charge. So that means, I'm going to put the 1 here just so you don't think it's a dash. It has a negative 1 charge, so that means it gains 1 electron. Aluminum is in group 13, so it has a positive 3 charge. So that means it loses 3 electrons. And then oxygen is in group 16. That means it has a negative 2 charge, so it gains 2 electrons. So the charge, if you can figure out what that is, that tells you how many electrons it loses or gains. All right, so the next one, it says write the name and symbol of the ion formed when a potassium atom loses 1 electron. Okay, well, potassium is K. If it loses 1 electron, it has a positive charge. Since it's positive, we just call it potassium ion. All right, then it says when a zinc atom loses 2 electrons. Well, zinc is Zn. If it loses 2 electrons, it has a 2 positive charge. And since it's positive, we just call it zinc ion. Remember, for positive ions, you don't change the ending of the name. And then part C, a fluorine atom gains 1 electron. So fluorine is F. If it gains 1 electron, it has a negative charge. Since it's negative, instead of calling it fluorine, I'm going to call it fluoride ion. Because remember, negative ions, we have to change the ending to I. And then the last one says, write the electron configuration for CD, positive 2. Okay, so first I'm just going to write it for CD. Okay, so I'm going to start with hydrogen, so 1s2, then lithium, 2s2, boron, 2p6, sodium, 3s2, aluminum, 3p6, potassium, 4s2, scandium, 3d10, gallium, 4p6, rubidium, 5s2, yttrium, 4d10, yttrium, 4d10, because we're ending at CD. So this would be the original electron configuration for CD. Now, before I start taking into account the charge, I need to rearrange. But notice I have 2 spots that I need to rearrange. Okay, every time you hit a D or F sublevel, you're going to need to rearrange. All right, so see, I hit 2 different D sublevels, so I need to fix 3D and 4S. So 3D10, 4S2, and I need to fix 4D and 5S. 4D10, 5S2. So now I can take into account the charge. So positive 2 means it lost 2 electrons. So I go to the highest sublevel and I get rid of 5s2. So I don't take them from 4d, I take them from 5s. Alright, so hopefully you're finding the beginning of chapter 7 to be pretty easy. There is a part in chapter 7.2 called balancing charges that is super important to get you through the rest of this entire class. So please make sure you pay attention to that part.